eventually. I will try to talk loud today. I think I talk loud anyway, but my batteries are dead in the microphone, so for the recording it might be a little iffy, but hey, that's the nature of life. I apologize. Today, I didn't ask you to do any reading ahead of time because we're going to try to cram a whole bunch of stuff into the second to last lecture. So congratulations, you're down to 2 lectures left. There's not much time left. Next week, I'm going to talk about glass. We're going to test your little trusses. I will give you a practice test that you can take home and work. If it's not already, it's probably posted on the website, but I'll make sure it's posted so you guys can download it and practice it. Very much the same format as before, just a little bit longer. You'll have the full 3 hours to do it. Obviously no notes, all the same stuff. You need the same Scantron, whatever that green one is. That's the 200 question one. More of it will be on wood because it hasn't been tested, but it will review everything else, just like the last one reviewed concrete. Does that make sense? So it is cumulative. But the emphasis will certainly be on what we haven't covered yet. I passed back your test corrections. Pretty much everybody that did test corrections got at least some points back. If I didn't get to yours, I'll pass it back at the break. I passed back quizzes from last week, so you should have those. I passed back grades from the steel assignment, so you should have those. Is there any other major announcements? I don't think so. Okay, so today is a bit of a long one because we're trying to kind of cover the things that we haven't covered yet. The good news is a lot of it's fairly easy to get through, so it shouldn't be too bad. So we're going to start with chapter 6, then we're going to do chapter 7, and then we're going to, I think it's chapter 16, but my notes when I was reviewing them said that it might be chapter 18, so I'm not sure which chapter it is, but it's the roofing chapter. So we'll have to double check on that one. So let's start with chapter 6. This is exterior finishes for wood light frame construction. So we spent last week covering, what is light frame construction. You had a quiz today reviewing the terms from light frame construction. But the primary purpose of exterior cladding is to protect your building from the weather, right? We have to find a way to shell our building in such that these kinds of conditions don't get from the outside to the inside. So everything that we do is designed around that basic principle. Okay? So let's start with roofing. Okay, we're going to kind of go through roofing a little bit here. I'll go into roofing in far more depth at the end of the lecture. But before you can shingle a roof, we need to finish the eaves and the rakes. So when we work our way up, okay? So by eaves, I mean this part here. Rakes, I mean the pitched part, okay? And so when we layer up our roof, right, we have to make sure that when water or snow or rain falls on the top of the roof, everything that it comes in contact with at the next layer is always underneath the first layer. So if we start all the way at the very top, that's the last thing that you'd apply. Okay? It'll make more sense as we go through. Okay, a little bit of terminology about roofs just so that when we're talking about it, we can be consistent. Okay? We have a gable, which is the end here. Okay? The diagonal piece is called a rake. If you have something where 2 slopes of a roof come together and meet, it's called a valley. Okay? If the valley is kicked out the opposite way, okay, where you have 2 slopes that meet on the outside corner, it's called a hit. Okay? An eave is the flat edge along one side of a roof. Right? So we have a rake and an eave. These are less important. Dormer is just this little window that pops out. Okay? Mansard is just this type of roof. Ridge is what goes across the top. We talked about a ridge board and a ridge beam last week, so it should be somewhat intuitive that they're there. There's always going to be some form of vent relating to the roof, and we'll talk about that as we get into roofing. So this is a roof rake, right? This is a sloping edge condition, and I'm just showing you what this picture is so that when we see the drawing, it'll make some sense. Okay? So this is the drawing that relates to that particular picture. And so like I talked about, it's always from the top down. Everything has to be layered underneath. Okay, so if we start here at the very top, right, recognize this is just a cut through a sloping roof, so it's sloping away from us. Okay, this little piece is the actual roofing. Tucked underneath that roofing is this metal drip edge. Always has that little flange that kicks out, such that if water were to drip down here, let's see if I can point to it, and I'll use laser pointer. Okay? If water were to drip down over the edge, it would come down here, and since this little piece kicks out, it's always going to drip off the end rather than go back up into the building. It's not going to wick back into the building. So that's why it's called a drip edge. Okay? Underneath that is the rake board, and then we've got the siding. So if we jump back here, this was our siding. This piece here is called the rake board, so that's the piece that you actually see in terms of trim. Another example here. This looks very, very similar. Okay, where we've got our rake board here, and we've got our trim, and finally our roofing. The difference is that this actually extends out as opposed to being flush with the siding itself. So the detail's slightly different. Similar, okay, but slightly different. In this case, we have something called a lookout that spans from one rafter in out, so that, remember, if we have a cantilever, right, we can't just have this piece floating out in space and fall off the building. So we need something to support it. That's called a lookout. We have our fly rafter, which is the outermost rafter, right, followed by our rake board, our metal drip edge, virtually the same detail that we just talked about. Okay? So when we think about designing roof edge details, okay, the edges of the shingles should be positioned and supported in a way that water flowing over them, right, will drip free of the siding and the trim below, right? So it's always about creating an edge for water to drip off, okay? So we never want to have a condition where water can work its way back up into the roof. That's the key thing to understand. Okay, so we're always going to overhang that roof just a little bit, such that if water comes to the edge, it's going to drip off rather than wicking back underneath. Okay? The other thing is that eaves need to be ventilated to allow free movement of air, right? So we don't get condensation and we don't have mold and mildew growing inside the roof. So there's going to be a variety of ways that we're going to deal with that. We'll talk about each of those in a little bit more depth. Okay, so this is the eave. This is the flat part of the roof, roof, right, that goes along the length of the building. In this instance, we have the same thing where the shingles come down ultimately to a metal drip. Again, same piece of flashing, right, so that water comes down and drips off into this little gutter. Okay, this is our rafter. Okay, when we put the insulation in for our ceiling, there always has to be this little airspace that allows the air to come up through the vent here and along the roof itself. And I'll show you why in just a second. Okay, if we don't have that fascia board, right, and this comes down to a nice point, same concept here, we don't have the metal drip edge in this condition, right? But notice that this shingle, this last shingle, comes to a point anyway, so it acts as its own drip edge. This is not very common. I haven't seen this too much in practice, but it is a way of actually making the vent, or making the eave. Okay, so this is a photograph of an eave. You can see that we've got the continuous vent running through. In this instance, we've got our shingles hanging out over the edge, right, such that the water's going to drip off there. Make sense thus far? Yeah? Okay, another example. Okay, very similar, same kind of a little metal drip edge. This is an aluminum gutter. You don't need a gutter, but there's a gutter in this instance. Side note, if you were up in, say, Lake Tahoe, would you put a gutter on a building? No. Right? Bad idea, because the snow is going to rip it off the building. So if we're down here where we don't get snow, gutters are really nice because we can deal with channeling all the water that comes off our roof, put it into a pipe, and get rid of it. Okay? In the Sierras, you have to deal with the water that drips off the roof at the bottom rather than up here at the top because the snow will take that off. So just important to consider, depending on where you're designing or where you're constructing a building, you have to pay attention to that kind of detail. Okay? In this instance, there's an aluminum fascia here that's wrapping what would be the fascia board. It doesn't really matter whether it's a wood board or it has an aluminum coating. The principles are all still the same. We also have this space here. Recognize the insulation is lower, such that air can get out through along the ridge. Okay? So why is that important? Why is that air important? So this is called an ice dam. Okay? And it doesn't happen so much around here because we don't have lots of snow. Okay? But if we are in an area with snow, we have to pay attention to where the heated air is versus where the cold air is. Okay, so in this condition, right, we have heated air that's on the inside of the building here. Recognize there's no insulation in this particular example. Okay, and so the heated air is heating your attic space. Okay, but out here in the eave, there's no heat getting to that particular portion. So if snow piles up on the top of your roof, okay, it's going to melt
where it's in contact with the heat, but it's not going to melt out here where it's not in contact with the heat. So this snow that doesn't melt is called an ice dam, okay? And it traps water, right, in between the ice dam and the rest of the shingles. And what happens is the water gets deep enough so that it goes up under the shingles and comes down and drips into your walls, okay? Which is really bad because you get mold and you get water in your walls and all the kinds of things that you don't want to have happen. So you have to pay a lot of attention to what happens. So this is the ice dam condition, right? We've got melted snow above, we've got the ice dam below, water's getting into our building. That's a bad thing. Okay, so we want to avoid that. So how do we avoid that? Okay, if we pay very careful attention to how we insulate our building, we can avoid that. So in this condition, right, we have a flat ceiling inside our room, our ceiling's been insulated, our walls have been insulated, it's containing the heat within the room. Okay? But in doing so, we also need to make sure that cold air can run all the way up the length of the eave, the length of the rafters, okay, such that it's always cold against the snow. So you've got cold air coming in from outside, running up along here, right? The snow is always cold, there's no ice dam forming because it's all the same temperature. Make sense? Pretty easy way to do it, okay? What happens if we have a vaulted ceiling of some sort? Okay, a lot of times you want a vaulted ceiling. So we're heating the area inside. We've used the insulation in here. This is fiberglass bat insulation. But we have a channel that allows the air to go along, right, the length of the rafters here, right, such that it maintains that cool layer, which causes the snow not to melt. So it's virtually the same concept, except the insulation's tipped up so you get the vaulted ceiling. Make sense? Okay. The other option, if you run into this trouble and you haven't insulated well enough, is you can run little heated cables along here, and you'll see this in a lot of older homes. You go up in Lake Tahoe and that sort of thing where they haven't dealt with this, okay, poor insulation. They'll run the heated wires such that the ice dam can't form because they're actually heating where the ice dam would form and causing the snow to melt. Okay, so it's the inverse approach, right? You deal with the problem this way as opposed to building the building correctly in the first place. Okay, but you can do it that way. Problem is, what happens if the electricity goes out? Right? Then you get the ice dam and then you have water in your building. So you're relying on a lot of things. So to make sure we have that proper space running along the interior of your sheathing of your roof, right, a lot of times we'll actually nail in these kinds of plastic baffles, right, that maintain that airspace and that circulation for us. So this would be if we're applying the insulation in between our joists, right? We don't want to accidentally have the insulation fill up that gap. We need to maintain that space. So we're going to actually nail these into place. Okay? Sometimes you'll have a roof vent that occurs at the top of the gable. Okay? Sometimes you'll have, along the top of your ridge, you'll have a vent that's built into the shingle system, right? So that air can actually come in, work its way up and out. Sometimes it has to go out one of these vents. It depends on the design of the building. Okay? But the idea is that if you have those eave vents that allow the air in, obviously you need something at the top that allows the air out, right? So you get that flow and that circulation. So in this instance, right, it's coming out this side vent. If we had a ridge vent here, it would be coming out the very top. The ridge vents tend to be the most energy efficient, right? Because as the hot air comes in, it rises, it goes to the very peak, it comes out, cold air comes in to fill it out, etc. Right? If you have it like this, there's always a bit of hot air that stays at the very top. So it's not quite as efficient. Couple other options for insulating. In this instance, right, recognize we have the warm side here. Okay? We're using insulation, rigid foam here. We're using our insulation. Note that this is coming together. The insulation here passes, right, through into the eave. Okay? So we've got a nice joint, right? There's our hot air. This is all insulated. So everything outside is equally exposed. Okay, there's no place for the ice dam to form. Okay, same thing here, right, where the insulation is continuous down into the wall, right, such that this can continue. Okay, application of roof shingles. Again, we'll talk about this a little bit more later on. So the thing about roof shingles is that you have to start at the very bottom of your roof and work your way toward the top of the roof because they all overlap. So in this condition, right, we have one layer here. The next layer is applied half on the previous layer, half off the previous layer, and then you keep working your way up. Okay? So it has to work like that for us to have good water. Questions so far? No? Okay. So now we move from the roof and kind of the roofing details to how do we seal off a window opening. Okay? And so you can see that in this sort of a lecture, right, we jump around and we try to cover a whole bunch of how do you seal up your building. Okay? And that's kind of the way the book does it. So this is installing windows. And there's a couple different methods for installing windows in terms of how much flashing you do. Generally, if I were saying how to do a window, I would over-flash rather than under-flash. The more flashing you do, generally the better. But it's going to vary a little bit. So the book's example doesn't do very much flashing, so this would be kind of the minimum flashing. So what happens is, we talked about in the Lightwood frame lecture, is we're going to frame in our rough opening. Right? Our opening like one of these over here, right, where we have our headers. Supporting our header are our trimmers, right? Then our king studs run along the outside, right? We have our cripples and a rough sill. This is the rough opening of the window. So we need to figure out how do we apply that window into this rough opening. So if we think about water, water is always going to flow down due to gravity, right? And it's going to come out. Right? We don't want it to go into the building. We need it to come out at some point. So when we think about installing a window, we have to start at the bottom of the window, right? Because, we don't want water to go in. So we're going to start at the bottom, and we're going to flash across the bottom, right? Wrap it into the sill of the window and also up the sides, usually 6 to 8 inches or so. Okay? So we're creating this nice joint. Usually you're going to do it in 2 pieces and lap the corners. The book doesn't show it that well. Okay? So we're going to do that nice detail here, such that any water that comes down the window is definitely not going to go into the framing, but it's going to come out, right, along this. After that, I know it's really hard to see in this, but this is out of the book, so you can reference it later. We're going to run a bead of caulk around and leave it open at the bottom. So there's no bead of caulk at the bottom, it just goes around the windows. Okay? In that instance, right, when we put the window in, any water that comes and hits the window from the sides or from the top is going to run around the window and ultimately out over this flashing at the bottom of the window. Does that make sense? Right? So we're working on layering it up. After we've done that, we're going to take our window and we're going to tip it into place, okay, against that bead of caulking. Right? Then we're going to plumb it, right? Level it and plumb it. And usually in a vinyl window, this happens to be the stereotypical vinyl window. Some aluminum windows are like this. Depends on the complexity of the window. But usually for new construction, it's going to have these flanges with a whole bunch of nail holes. Okay? Once you put this into place, you're going to drive nails through those holes to hold it in its proper location. So a rough opening of a window, like we saw framed in that model or any of the models that are around here, is usually going to be about a ½ inch bigger than whatever the final size of the window is. Okay? Or I should say, the window's usually a ½ inch smaller than it says it is. Right? So if you order a 4030 window, it's actually a ½ inch smaller than the 4 feet. Right? So you're at 47 and a half instead of 48 inches in width. So that's always going to allow the window to fit in here. Okay? So we've done that, we've nailed it into place, and then after we've done that, we're going to cover the sides with flashing. Right? And then we're also going to run across the top with flashing. Again, in that order, sides first, then top. So any water that hits the top can roll onto this layer, which comes down here and rolls on top of the layer below it. So it's always about making sure the water gets pushed further out, away from the surface of the building, right, rather than getting trapped and coming in. If we did it in the opposite order, the water would go in toward the building. Make sense? Okay? So this same thing can be applied to a door, right? Same kind of flashing around a door. Obviously, you don't start at the bottom because the door doesn't necessarily have a bottom. It depends on the threshold. So here it is in actual practice. Okay, so we're seeing this condition, and again, every time you do these sorts of things, it's always slightly different. Okay, depending on who the contractor is. In this instance, we have our Tyvek right running underneath. They've actually flashed underneath the flange here, so they have an extra layer of flashing. It's not necessary. If I were doing a window, I would do it this way and then flash over it, so you end up with a couple layers of flashing, under and over. It just depends on who's actually doing the window and how much you want to make sure it's watertight. Okay, another example here. So this doesn't have any flashing around it yet. Here we have, in this instance, we've wrapped our house in the Tyvek wrap. We're using a Vichatang, which is a kind of a rubberized material. We'll talk about it a little bit more in the roofing lecture. But it's a rubberized bitumen. It's kind of like a tar. That would be the best. It's kind of like a cross between rubber and tar. It's kind of weird. Okay, it's sticky, but it's a very good sealant. So they wrap the bottom sill first, right? Then they're wrapping the sides. Then they're wrapping the top. Okay, so it's always in that order. Then they're going to apply the window in between.
Hey, Grant,
Yeah.
on that last one, the first one, they don't have anything on the bottom.
In this here,
Yeah.
my guess is they do have something, but it's hard to see. It's probably very short. This would make me nervous if it was my job. Okay, I like when it comes to something like a window, right? That's almost always the most likely place in your building that you're going to have a leak. If you're going to have a leak, obviously the roof is another big example. Okay, but if you have water beating against something like this, right? We need to make sure that the water gets out. So the more flashing you have and the more carefully you do it, the better off you're going to be long term. So if this does have a little bit of flashing, which it must, otherwise I don't understand why this would be an example, but if there wasn't that little 1 inch, then it would be a big problem, okay? If there was just that 1 inch, I'd be nervous personally, because I'd be wanting a little bit more, because this is draining directly on plywood. So I'd be getting nervous about it, but that's good observation. This is much more my style. Okay? So the same thing happens, let's say you're redoing the windows in your house, okay, and you have existing windows. If you tear out an existing window, you have to find a way to do all this flashing again. Okay, so you want to think through the same concept, where you start at the base, and you wrap the base, and then you work the sides up. Okay? It can be challenging, but that's how you ensure that your house is actually watertight. Okay, so installing doors. Doors are very much like a window. Right, we have our header, we have our 2 trimmers supporting our header, okay? And we need to install the door in between that particular opening, that rough opening. Now the challenge with doors is actually trying to somehow explain how this works, okay? Because the only real way to show you how to do installing a door is to install a door so that you can see how it kind of goes together. But what happens is you've got a couple of varieties. I'm going to walk to the back and use this door here is a bit of an illustration for us. Okay, because it's kind of the closest thing we have. I can't use one of these doors as part of the partition. Okay, but you have your door itself. Okay, I know you guys have trouble seeing that. So you have your door itself, and depending on the type of door you order, it can come what's called pre-hung, or it can be something that you have to hang yourself. If it's pre-hung, it's going to include both the jambs, okay, so this part and this part, as well as the top, along with the door. It's already going to have the hinges. Already going to be assembled into one unit. Usually there's a few nails holding it for shipping. Okay, that's a pre-hung door, which tends to be relatively easy when it comes to actually hanging the door. Okay, if it's not a pre-hung door, you have to make all these jambs. Okay, which takes some skill, and I'm not going to go into the details of how you do it. Okay, in this instance, we'll assume for a second that it's a pre-hung door. I would open the door and talk, but they have a meeting next door, so I can't do that. Okay, so if we're putting this in, right, there's going to be a rough opening in this wall that I'm going to have to put the door into place. Okay, so it's going to look very much like this, right, where I have my trimmers on either side and they're supporting a header. Okay, same thing here. That's going to be wider than the jambs that I have that are attached to this pre-hung door. And so I'm going to need to have some kind of spacers on either side such that I can adjust, right, and fill up the gap so that if I nail through this jamb, it's going to be able to attach to the trimmer on the inside. Does that make sense? Okay? So what happens is, I'm going to use 2 shims, and shims are basically shingles that are cut into little thin strips. And I'm going to use one from one side and one from the other side. Okay? So the 2 fine points are going to be pointing at each other. And when I push those 2 together, it gets a little bit thicker and it fills up the gap. Does that make sense? Okay, so I'm going to insert one from one side and one from the other side, and that's going to help me fill up the gap. Okay, and it takes a little bit of practice, it takes a little bit of art to do it really quickly and efficiently. But I'm going to start with the side with the hinges on it. Okay, I'm going to insert those shims in, and I'm going to make sure that that side is nice and level, or plumb, excuse me. Okay, and I'm going to fasten that side to the trimmer on the inside. Jack stud trimmer. I use trimmer, it's just habit. Okay. through that trimmer with those little spaces, okay? Then I work my way around the door, okay? And so I can adjust the top. Usually I don't adjust the top until later on, but I'm going to start to adjust the opposite jamb, the one where the latch is, and I'm going to again use those shingles, right, to pass one another, okay, to get that adjustment in thickness, okay? And that's going to, maybe it takes 3 shingles, maybe it takes 4 shingles. It depends on how wide the rough opening is and what the size of your particular door is, okay? Now the challenge here is that I need this to be plumb as well as this to be plumb. I need this to be level across, right? So I'm a lot of times going to put shims underneath the bottoms of the door to help level them, okay? Then on the other side, if they weren't having a meeting, I'd make you all go in that room so you could see, I would look at the margin of the door. We use this as an example. I would look at the margin of the door here to make sure it was nice and even all the way from top to bottom. Okay? Same thing across the top here. So if I were hanging a door inside a house, this would bother me that this margin is different from this margin. Right? So it's all about, you know, how good of a craftsman you are in terms of those kinds of details that you can pay attention to. If this is totally not the right foot. Stay. Okay. So, I'm going to put those shims in on this side. Now, if I put too many shims in, right, this is going to be too tight and the door is going to stick. Okay, if I put too few shims in, right, this isn't going to be nice and parallel to this side, and I'm going to end up with a really wide gap. So, it takes some skill to be able to do it correctly. Okay. Luckily, we have nail guns, which helps in this day and age. If you were hand nailing it, it'd be even harder. Okay. After I've done that, and so I have the inside jambs on, then I'm going to apply the outside casings. Okay, these pieces of trim boards, right, that go around the door itself, and that finishes it off so you don't see the gap in between. Okay. Yeah.
So you would plumb the sides and then you would do the top?
Yeah, it's kind of it's a weird combination of you've got to do it all kind of at the same time. So you would plumb the 2 sides and make sure that they're correct. Then you'd be checking for level, but you'd also be comparing the door, right? Remember, you've already attached the side with the hinges on, so the door is hung there, okay? And sometimes you do it independent of the door. You take the door off and you put this side on first to begin with. Then you put the door back on, okay? But I'd be swinging it closed, make sure the margins are nice and even. I'd be adjusting that bottom, put a shim in the bottom to jack up this jamb so that it ends up level, right? And so you're playing with all those different variables. Now, if your house is out of plumb, right, you've got other issues. So the other thing that can happen, and right, which distinguishes the craftsmen that are really good from the ones, how many people have a house where you open a door and it always closes? Right? Or a door, if you don't latch it all the way, swings open? Right? Very common. If, right, I talked about making sure this is plumb, but if the jamb isn't plumb in this direction, the door is always going to swing open or swing closed. Right? So you're doing all of these variables all at the same time, which is why hanging a door takes a lot of skill and practice. Okay? So you need to kind of work through it a little bit. If you're doing an exterior door, it's very much the same thing, except that the door is designed slightly different in terms of the jambs. Okay? In this instance, calling it a door frame. Okay? It is a jamb, but it's notched differently, right? To make sure that you have weather stripping such that when you close the door, right, it actually seals. Right, as opposed to an interior door where you don't have those kinds of things. So it's going to vary a little bit for exterior, but it's virtually the same thing. The other thing about exterior doors is they typically have a threshold below that you step over. Okay, that threshold keeps the water out at the bottom. Yeah.
So you say the jamb in the frame is the same thing, so the whole frame around the door is the jamb?
They're referring to the frame around the inside of the door as the door frame. I always refer to it as the door jambs, just for clarity, okay? Because I think, to me, door frame could be easily mistaken for the trim that goes around the outside of the door, kind of like a picture frame. So I get the two, I find the two a little confusing, so I'm always going to refer to it as the jamb.
Door or no?
What?
Do any of the door jamb at the top or just on the side?
The jamb can go across the top. What it is that interior piece, okay? The casings are what go around the outside. Okay. A couple other examples here, right? Again, we've got our trimmer. These are our little wood shingle wedges. All right, I call them shims. The book calls them wedges. They're kind of the same thing. If you go to Home Depot, you're going to buy shims. They don't sell wedges. Whatever. Okay? One going in from either side. again, to fill up that gap. And that gives you some flexibility if, for example, right, the framers who did the job didn't quite get the trimmers square, right? So you can fill a little bit more on one side versus the other side. It's all practice and skill. Okay? Okay, so let's talk a little bit about the siding on the outside of your building. So we've got a variety of different sidings. This is again out of the book. I'm just going to run through them so we can make some sense of them. We've got a plain bevel siding, which is basically a board that's been tapered. Okay? They lap over each other, right? So we put a nail through. The one below tucks up underneath the one above, such that if water comes down, it's always going to drip off and run all the way down the siding. Okay? Same thing happens in the rest of these. This is a rabbited bevel. It just means that there's a notch out of the bottom that the other one sticks up underneath it. Okay? We have our V shiplap, which is the same concept, except it's a flat board, right, that has different notches on the top and the bottom, such that they can lap over one another. Okay? We have our cove shiplap. Okay, same concept, just a slightly different variant of it. We have our V groove or our tongue groove here. Again, very similar concept, very common. This works even though, right, you guys should be questioning this, right, because this doesn't extend out, it goes back. So if water came down, it would flow back. But because the tongue sticks up, right, it can't flow back up and over. It's going to still continue to flow down. Okay, so it's a little nerve-wracking there, right? And this is a board and batten. The difference between this view and the other views is that this has been shifted up into a plan view, right, and cut. So we see our cut studs here. We're looking down on it. There's a board. The batten is over the top of it. If this were in the same orientation as one of these, right, the water would come in and go in towards your building, and that wouldn't work. Does that make sense? So it's important to note the difference there. Okay? So the other thing that's important to talk about when we talk about siding is the idea of using a rain screen rather than just relying on the siding itself. And so this is something that's very important, especially in stucco, but it is used in wood siding. If you're worried about water penetrating through your siding system, whatever it is, right, you can actually build a waterproof barrier right at the sheathing level, okay, instead of relying on the siding itself. So in this instance, we have our waterproof barrier back here. We have our little furring strips here, and we've applied our siding to the outside of the building so that if water happened to get through whatever the siding is, right, it would run down our waterproof barrier on the inside of that. Okay? So it's just a different way. It's called a rain screen. Just another way of doing it.
Is there a way out for the water?
At the bottom, there's always a way out. I don't think I have the detail here. It's too hard to see, but there's a gap at the bottom that allows the water to come out from the rain screen. Okay? So then we move on to plywood siding, which is typically T111. Any people heard of T111 before? You've probably seen this siding on a building before. Okay? From an architectural perspective, it's probably the ugliest siding ever. I hate it. But it is the reason that people really like it is because it's cheap and it goes up really fast. Because you're applying big 4x8 sheets. The thing about it is you're limited in the height, right? It comes in a 4x8 sheet. Maybe if you're lucky, it comes in a 4x10 sheet, okay? So you're limited in height. So if you have a 2-story, right, or 1.5-story building, you have to deal with that joint. And that's what this is dealing with here, okay? So we have one plywood coming up. We need aluminum Z flashing, right, which is basically flashing that forms a Z that goes underneath one, comes out, and over the top of the other, okay? So that any water coming down is going to be carried away, right, and onto the front of the next piece down, okay? So the point is, whenever you are using a plywood siding system like this, there will always be bands, horizontal bands across the building at 8 feet, right, at 16 feet. There's nothing you can do about it, okay? So that's one way of telling if the siding is, in fact, designed in that manner. So then we have shingle siding, and shingle siding is exactly what you think it is, okay? It's tapered pieces of wood, one slides underneath the other. The thing about shingle siding is that it varies in its width, and so when you vary in width, the vertical joints are always going to be staggered, which is why it works, okay? So that water seeping through one of these vertical joints will hit the flat part of the board underneath and still run down. Okay, so it's a system like that. Okay? The important things to consider are how do you deal with the interior and exterior corners of the building. So if you want a very beautiful building, you're going to go through the labor, right, of doing this kind of a treatment. Okay? Which means that every one of those corner shingles has to have a slight bevel on it that matches the shingle on the other side. Okay? So you're actually cutting this end shingle, right, on a diagonal this way to match the slope of the shingle on the opposite side. Then you reverse the process on the next shingle up. Okay, so they always overlap at the corners, but it takes a lot of extra effort to cut all those corners nicely. Okay, same thing happens on an interior corner, except you're cutting that piece in a different direction. Okay, so that they can continue to overlap. The result, however, is a very nice clean corner, right, where the shingle bands run all the way around. There's an easier way to do it, but it doesn't look the same. Okay, so before we move to that, I want to show you a couple architectural examples. This is Peter Zumthor in Switzerland. This is the St. Benedict Chapel. It's a really good example of shingle siding. This is a little church. If I can move forward, right, you can see it. So again, we've got that lapped corner appearing here. The nice thing, since all of the individual shingles are small, right, we can very easily do this kind of a curved shape. Right? We're not bending the boards themselves. They're still the same square normal boards or normal shingles that we're using. They just happen to follow the contour of the wall itself. Okay? This is what it looks like from the inside. Good example of light wood frame construction. Okay? This is it in context. Okay? And a little dirt road to get there. I mean, you know, great architect designs this thing and you have to take a dirt road to get there. Very cool. Right? But this is the Swiss Alps. It's a really nice setting. Here's an example of the light wood frame construction that he's using. He's playing around a little bit in that he's holding the exterior sheathing off, right, with these little metal brackets, as opposed to keeping it right on. But these are all light wood frame members, except for your beams and your ridge board. Another example is here, in the corner. Okay. So if you don't want to go through all the effort of lapping those shingles and cutting those shingles on the diagonals that they need to be cut on, right, you can put two trim boards in the corner, and you can put a trim board in the interior corner and shingle in between the two. Okay, so this is a lot easier. All the cuts are straight. You can apply the shingles much faster, but it means that you have these corner boards that run up the outside. So moving forward, when you go around and look at shingle buildings, right, you'll say, you did the cheap method, right? Right, so you'll be aware of that, and you'll have an appreciation for the labor that's involved in doing an actual lapped corner. Okay, so it's all in cost. So here we are, we have somebody doing the lapped corner, right? And then in this instance, they're actually replacing a set of shingles, right, where they're tucking up under the old shingles. But the concept is the same. So if you're laying your shingles, you want all the butts of the shingles to stay in a nice line. So what happens is you're actually going to attach, right, a board underneath, right, and then lay all the butts of the shingles on that board such that they're all lining up correctly. If you try to do it freehand like this, if you don't have really good skill at eyeballing, right, it's going to move up and down, and it's not going to be the same result you want. So it's much better to have this guide board that's attached to the building itself. Okay? So the nice thing about shingles is we always think of shingles as the typical texture, but they can really vary in terms of what they look like. The concept is the same, whether you have different shapes or not, right? If these were all flat bottoms, it'd be the same concept as if you have these fancy fluted edges on the bottoms, right? So you can vary the shingle texture quite a bit. So again, the key part of this is that the shingle itself is much longer, right? One shingle would be from here, right, down to here. Okay? And so if water fell in this crack, it would continue down along this shingle. Okay? So you can have this joint here and this joint here. The joints are always staggered. Okay? This happens to be an even stagger, right? Some of the other examples, some are wider, some are smaller. You just want to make sure that two verticals don't ever line up. Another example of texture. Again, we're varying the bottoms of all these. Same concept here. Another variant, again, you can see that this is virtually endless, right? Different ways you can do this. Okay, so let's talk a little bit about brick cladding on a building. Okay, so we're moving through our various methods. I have one drawing here that kind of explains brick cladding. Okay, so what happens with brick cladding is we have our traditional wood frame building underneath. Okay, we have our plywood sheathing. Then attached to our plywood sheathing, we have little, and this depends on the actual method for doing this, but basically we're going to have metal brackets that extend out into the mortar joints between the various courses of brick. Okay, it's usually every 3 to 4, right? In this, it's not, it's only showing us 1. Okay, and that's going to tie in this wall to the actual wood wall underneath. Okay, the key thing to realize is that there's usually a half, quarter maybe, usually a ½ inch gap that's actually air. So this is much like a rain screen, because remember, brick less so, but the mortar that's used to actually attach the brick together, right, is permeable to water, just like concrete. So water can actually come in through here, and we need to make sure that it can get down and out without causing rot in the building itself. So there's always that air gap, so that water that comes through will come down, right, and ultimately come out. There's a note for weep holes here, which is allowing that water to actually come out before you hit the solid brick that's attached to the foundation. Make sense? Okay, so that's for a brick veneer building, which is very, very common. The other thing that's common is stucco. How many people have a stucco house? Okay, very common around here. California tends to like stucco. Stucco is basically a Portland cement plaster. Okay, it tends to be really strong. It's very durable, right? It's easy to make, and it is a pretty fire-resistant material. So that's a good thing. Okay, it's usually applied in 3 coats over some kind of a wire lath. Right, you need something that's actually going to hold the stucco to your building. It's usually chicken wire, and it can be applied by hand or by spray. Okay, in this instance, he's applying it by spray. There's his little spray gun. Usually, it's finished with a trowel. Okay, the thing about it is, it's better if you use it with a rain screen system. Right, so you have the impermeable layer underneath the stucco, because how many people that have a stucco house have cracks in their stucco house? Right? Very, very common to have cracks in your stucco house, so water is going to get in through those cracks, so you need that rain screen underneath that causes the water to come down and out rather than into your building. Okay, so it's just something to be aware of. It works because you have that rain screen layer. If you just had, right, the actual plaster, the actual stucco on the outside of the building, water would go through and into your building itself, so you need that rain screen underneath it.
How do you avoid or eliminate cracks?
In stucco? Depends on the additives that are put into the stucco. It's kind of like concrete, right? Where if you don't engineer the building correctly or you don't do the mix correctly, you're going to get cracks. If you design the building correctly with the proper expansion and contraction joints, you can avoid most cracking. We do live in California. Things move around. You're almost always going to get cracks at the headers and that sort of arrangement. It's just the nature of the material. Okay, so in ending with our exterior finishes of the buildings, I want to show you an example of kind of where you can extend cladding. Okay, so this is a brick cladding system, much like the one that I showed you earlier. These are the floor plans of the various buildings. This is the computer kind of rendering sketch of that. Okay, and this is what they look like. Okay, so it's a brick system, right, that's doing the same principles that we talked about, but we're varying the architecture underneath. So if you were building one of these buildings, right, as a solid brick building, it would be very difficult. But since we have the steel structure underneath that can support the brick cladding, we can clad the building in whatever we want. Okay, so in this instance, for use of brick, we could use steel, we could use titanium, we could use anything else. Yeah.
Those could just be brick tiles, not full bricks on top.
It depends. I don't know this exact construction method. It could be just brick tiles that are applied. The concept is the same, whether they're brick tiles, they're thin, or whether they're full bricks. Okay, another example. Okay, and I'll show you one more. This is stone applied as a veneer. This is again Peter Zumthor. This is the thermal baths at Val's. How many people have seen this project before? A couple people. Okay. Well, I'm glad I'm showing it to you then. Okay. Again, in Switzerland, this is the exterior environment. There's a lot of special roof treatments because there's a green roof. All of these are stone veneers that are applied to the building. So the building inside has its own rain screen that causes the water to shed off. This is one of the private pools. Okay, with again that nice stone contrast to the water. This is how he treats the roof conditions. Okay, so at every roof edge, right, he's done this really great thing where he's left a little slit of light so it washes down the wall, which really highlights the texture of the cladding of the wall itself. Okay, so again, architectural trick, washing the walls with light. Okay, another example inside. It's actually, when you get into the plan of this building, it's quite fun because you can't get from one side to the other without going through some of the pools. Right, so you see, in this context, you're coming down, right, to get across this area, you have to come out. Right, so there's kind of a maze and a pattern. It has a lot to do with the process of taking a bath. But this isn't a design course, so we won't get into that too much. Right, I just want to show you the examples. This was one of the original inspiration drawings by Zumthor. Okay, so we'll keep going for a little while because we've got 2 more chapters to cover. We've got chapter 7, so we're going to keep going for a little while. So we'll start with chapter 7. This is interior finishes for wood light frame construction. So we just did exterior finishes in a nutshell. Now we're going to do interior finishes. Okay. So when we think about interior finishes, okay, a lot of what we're doing in the inside of a building is we're trying to cover up all of the utilities that we need on the inside of a building. So if we think about a building, right, one of the major functions of that building is to let us live within it. And if we're living within it, we need certain utilities that make our lives easy. Okay, and that's one of the benefits of living in the age we do, where we don't have outhouses and that sort of thing. So let's start first with a wastewater system. Okay, so we're getting to a little plumbing here. Okay, but if you need to get rid of your wastewater, let's say you turn on the faucet in your bathroom sink, right? You need to be able to get that water from the bathroom sink out into the sewer system or into the septic tank, depending on where your house is. Okay, around here it's usually a sewer system. So when I turn the faucet on, in this instance they're calling it a lavatory, we can call it the upstairs bathroom here, right? I need the water to be able to flow down, right, all the way out to my sewer. So I need a set of pipes that are big enough to accommodate however much wastewater I generate, right, that'll actually carry that water out the building. So there's a few little tricks that happen in the world of plumbing, okay? If I had just a straight pipe that connected from my bathroom sink out to the sewer, right, if it was like that, and I leaned over the sink, I would smell the sewer, okay, which wouldn't be the most pleasant experience, okay? So we've designed something that eliminates that, okay? So what happens is we have these little traps, and so you see these little horseshoes here. If you open up your bathroom sink, right, if you've never done this, when you go home, open your bathroom sink and look at the plumbing, right, you will learn very quickly. There is a little horseshoe, a U underneath, and what happens is a certain amount of the water that you turn on and that you use, a certain amount of that wastewater, sits in that little U and blocks air from coming up and out. Okay, so it plugs up the hole so you don't smell, which is really nice. Okay? So that's great. That's great. But if this were the case, right, and this connected straight down into the sewer, the problem would be that whenever you put water in, right, it would have to bubble the air out, right, such that it could evacuate correctly. So in this instance, right, we needed to avoid causing the water to get sucked out. So above in your bathroom, wherever your water ties in, there's always going to be what's called a vent stack that runs out to the top of your roof. And so that allows air in from the top to allow the water to actually flush all the way down and out into your sewer. Okay? So you need both halves. You can't have just the waste pipe running from the sink into the sewer. You also need that T that causes it to go up and out, right, on the top of your building to allow the water and the whatever else to flow out of your particular building. So the same thing happens in your shower. The same thing happens with all your toilets. The only difference is the size of the pipe. Okay, so depending on what waste you're getting rid of, you have to vary the size of the pipe. Obviously, as you get further down in the building, ultimately to where you connect to the sewer, the pipe needs to be the largest. Okay, because if you turn on all of your various faucets all at the same time, your sewer system still needs to accommodate all of that water and all of that waste. Make sense? Okay, so that's kind of how the wastewater system works in your house. Any questions about that? No? Okay. So, what about water supply? Okay, so when we turn on the faucets, we need the water to actually get there. Okay, so what happens in water is we're going to work kind of in the opposite direction. So in the sewer, we're getting rid of the water to the street, right? In the supply, we're getting water from the street or from the well, depending on where your house is, right? And it's coming in as one line. It doesn't come in as hot water. It just comes in as cold water, okay? That cold water comes in and typically runs very closely to directly into your water heater, okay? Now, in this day and age, we have some variety. We might have our regular old tank water heater. We might have an on-demand water heater, depending on how energy efficient our house was, right? And from that water heater, right, we run two lines, one hot and one cold, to all of the various fixtures in our house, except our toilets. Our toilets are just going to get cold. We don't need hot water to the toilets, okay? So all of our sinks and our showers are all going to get those two lines, the hot and the cold. Now, depending on how you actually design the system, you may run the cold to various fixtures prior to running it with the hot water. Sometimes you run it straight in to the water heater and then from there off with a pair, a cold and a hot. Just going to vary, okay? So when we're building our particular house, right, before we cover up our walls, before we put our insulation in, the first thing that we're going to do is put our waste system in, right? Biggest pipes take advantage first, okay? Maybe we'll do our HVAC. Depends on who gets the bid first and who gets let in first, okay? After that, we're going to apply our supply water system here to get to all the sinks. And then after that, we're going to do our electrical. And after we do our electrical, we're going to move on from there, okay? So this is our supply and waste systems in a particular wall. And sometimes it's beneficial to kind of have to see how much of this backbone needs to go into our walls, right? So when we're designing, it's so easy to think that, oh, we just have these cavities, we'll fill it all with insulation, and life will be good, okay? The reality is, a lot of our walls are full of this kind of nest of pipes, right, and waste. Both of these examples are using PVC for drain. Very uncommon around here. Usually it's going to be the black plastic. It's going to be ABS. Just depends. I don't know why they were using ABS here. Our supplies are typically in copper, though we're moving in the direction of plastic, which personally makes me a little nervous. I don't want my supply coming from plastic. I'd rather have it come from copper, whatever. It's just something to be aware of. So here we've got our framing diagram. These are for toilets here. These are our toilet flanges. And it's kind of showing us our waste system with our vent that goes out to the top, right? We've got our various toilet fixtures here. We've also got our supply coming into the bathroom. We've also got our drains. I know it's really hard to see here, but you can see it in the book. Later on, it kind of shows you how it all fits into the building. So beyond our plumbing issues, we also have our heating, ventilation, and air conditioning systems that need to go in. How many people know if they have forced air or some other type of heat in their house? How many people have forced air? I do. Okay, so by forced air, that means if you can see a vent in one of your rooms, you have forced air. Okay, so that's nice. Okay, so the idea behind a forced air system is that you have a furnace, could be in a closet, could be in a garage, and that furnace has a burner. We'll talk just heat for right now. That furnace has a burner, okay? It heats the air, and then there's a fan, and that fan blows the air into your various rooms, okay? Somewhere in your house, you also have what's called a cold air return, which takes the cold air and flows in a big pipe back to the furnace where it gets heated up again and thrown back out, okay? So the nice thing about this kind of a system is it's a pretty instantaneous system. You want heat, you can have heat. You to go turn on the thermostat, right? And then you pay your PG&E bill later and are really upset that you've turned on the heat. Okay, so this instance, this drawing basically illustrates that. We have our cold air returns on our various floors. It's coming down into the furnace system, right? The furnace system is then blowing it out to all of these registers, which is where all the heat shows up. There are some strategies for where you place the particular vents to make it more or less efficient. We'll save that for your energy class when you take that down the road. Okay? If we have an air conditioning system, it's very much the same thing, except that instead of the air being heated by gas or electric, right, it's going to be cooled by the Freon that's run through your air conditioner. Okay? I'm not going to get into the complexities of an air conditioner system. It's just enough to know that you have to have your air conditioner outside because it's exhausting the hot air, right, and bringing the cold fluid in to chill your air on the inside. Anyway, we don't have to get into the details. If you don't have a forced air system, you might have some form of a hydronic heating system. In this particular instance, there's a boiler. Okay, this tends to be for older houses. There's a boiler somewhere down in the basement. It heats either water or oil. That water or oil flows through a set of pipes up to what are called radiators, which are basically these little, they can be big, set of fins, right, that are usually iron or some kind of steel. The water flows through those fins and heats the air around it. There's no fans, there's no blowing air, okay? It tends to be either on or off, right? It's also very typical in an older building to where at a certain day of the year they turn the heat on, no matter what the temperature is, and then at a certain day of the year they turn the heat off. So it's much harder to regulate. You can't say, oh, I'm cold, let me go turn the boiler on. It doesn't work that way. It's kind of on or off, right? And it can take a while for the rooms to actually heat up because there's no fan blowing the air into that particular room. So some of you may be lucky and have what's called a radiant heating system. Anybody have one of these? I wish I had one. Okay? The idea here is that in a radiant heating system, you're applying heat right to the floors. Okay? So you're running it, and there's a variety of ways of doing this. Okay? These can be electric coils that run through a floor, right, that heat up and cause the floor to be warm. They can be a series of oil-filled or water-filled, usually with some kind of antifreeze in it, filled tubes, right, that run through the floors. You turn on the heat, right, it heats the water that circulates through the floor, right, or heats the electric coils, warms the floor where your feet are in contact, right, and slowly warms the lower half of the room, right, rather than heating the rest of the vaulted ceiling. So if, for example, you are in a building, right, where you have really tall ceilings, you're going to want to stay away from the forced air because you're heating a whole bunch of the air that you don't use anyway, and you're going to want to go toward a radiant heating system, right, where you're heating the zone, right, that's actually you're in contact with. The problem with a system like this is there's about a 3-day lag from when you turn it on to when you can actually get the room to be nice and warm. My own experience with this kind of a system comes from somebody who I used to work with up in the Sierras, and he had a house that had this system in. And he knew, he goes in there in the winter and does research and whatever, and he knew that he had a specialized system. He knew that he had to call in and turn the system on. He had it phone switched. So he could call in, punch a few numbers, and it would turn the heat on about 3 days before he would get there, and then the house would be warm by the time he got there. Okay? So you have to think ahead on a system like this. So it's the same kind of thing where it's either on or it's off. It's not, I'm cold right now, let me turn it on. Okay? But once it's on, it's a really nice heat to have. Okay? Which is why I said I would like it. Yeah.
Could you create a system that cools the house down using the same method?
Yes.
Ceiling?
Identical method. Okay? Yeah, ideally it would be in the ceiling rather than in the floors. And you'd be running some kind of chilled water through it. You could be Freon, though it would probably be too expensive to run that much Freon. One of the things that I have seen done, depending on where your climate is I've seen people take a ground storage of water, tap into that ground storage, circulate that groundwater through the building, and then dump it back into the ground. Or you can have a cavity full of water, some kind of a tank underground that stays relatively cold by the ground temperature, and run that through. Another example. Yeah.
So over a period of 5 years, what would be cheaper, a radiant heating system or like a central heating system?
Probably cheaper initially to install would be your forced air. The problem with a radiant heating system is it's usually encased in some kind of a layer of concrete, some kind of a lightweight concrete, so it's more expensive initially. Depends always on the efficiency of the system. So whether it's boilers heating the water, you're always going to be using some form of energy to do it. Some people will use solar, so not photovoltaics, but actually heat the water by solar, in which case it would be a lot less expensive to do the radiant method because you're circulating that water through. So it's always going to vary a little bit depending on the specific circumstances.
So it could go either way.
So it could go either way depending on the design of the system and how many pumps you use to circulate the water and how many exchangers it goes through and what have you. This is a little iffy.
How many combination, I wasn't gonna say anything at the very beginning, but we stayed at a cabin during the winter at Tahoe, and you walked into the kitchen and it's like, the floors are all warm, and bathrooms too.
Yeah.
But it also had forced air, so I was wondering, now I don't know if it was a combination.
My guess is, and this is very common, and I've done this in a few of those kinds of houses, and actually if I were doing it to my own house, I would consider this as well. You have a forced air system that you can turn on if you need that kind of instant heat. but then in a few select regions, specifically in bathrooms, it's nice. You can install a specialized hydronic heat system that's an electric mat that you actually put in underneath the tile of the floor. There's usually a separate thermostat on the wall that controls just that particular room. And it's pretty nice because if it's electric, it's pretty much instantaneous. You turn it on, the floor gets warm. Which can be a really nice thing in the middle of winter. You go skiing or whatever, and you can turn on the bathroom and the floor's warm. The nice thing about doing a bathroom is you're going to heat the area you're actually walking on, not the stuff behind the cabinet under the toilet. So really the amount of heated floor is only a couple feet by the length of the bathroom. It's just what you're walking on. So the next time you're at a cabin like that, put your foot over behind the toilet and see how warm it is.
Warm right there.
Yeah.
Because the radiant heat would be the entire.
The radiant heat tends to be the whole floor, everything. So a hybrid system would be something like that. My guess is it would probably be the electric. And they'll put it in typically under some kind of like tile or stone or something like that. And it can be really, really nice. Though, if you're using electric heat, it also tends to be more expensive. So when you get into your energy class, they'll talk about why electric heat is more expensive than gas and what have you. But at least you're aware of that.
Yeah, that's what I was gonna ask. Where would you place that? You would place it over the subfloor? You wouldn't place it where there's gonna be any insulation, you're gonna place it
Right, so you have to be...
underneath your actual flooring?
Exactly, exactly. So in this particular instance, like let's say this guy, right, where you're running the coils through the floor, you're going to put your subfloor down, then you're going to run all your coils on top of the subfloor, then you're going to pour lightweight concrete over, right, the subfloor basically, and it's going to be about 2 inches, and then you're going to put whatever your finished material is. I've seen cabins and stuff leave just the bare concrete floors.
Now, if you're gonna,
Some people, and, you know, they put dyes in them and they cast little leaves in them and whatever. But you can have that, or you can cover it up with anything else that you want.
if you're gonna do it that way,
Mm-hmm.
in constructing the house, would the engineers have to do something specific to actually hold that weight on?
Right,
something?
it's a lot of extra weight, so you have to anticipate all that extra weight that's going to be in the house. The other thing is you're going to at least double, maybe triple the bottom plates, because you've got that extra 2 inches of concrete before your actual plates start. So you're going to end up with an area of the house that's framed with the subfloor lower than somewhere else, unless it's consistent all the way across. But you're going to have to at least double up those bottom plates to make up for that gap. Okay. It also means that your bottom plates might be pressure treated because they're going to come in contact with water, and so there's a variety of things that you have to anticipate before you build. It's also not. It's not a platform frame where you build the platform and then you pour the concrete and then you build the walls on top, right? You build the house first, then you pour the concrete inside after all the walls are built. So it's slightly different, okay? If it's an electric system can go in the thin set. You put your tile backer down, then you put your thin set, and then you basically impregnate the coils in that thin set, and then you put the tiles over the top of it, right? So it's just a slightly different method. But the same concept. But obviously, if it's wires, it's thin, as opposed to these kinds of things, which are 3/4 inch tubes or 1/2 inch tubes. So you need the concrete around. Any other questions about that? No. Okay. So we move on from there into the electrical system. Okay, we're not going to spend a whole lot of time in the electrical system. It's just important to realize that you're going to have a variety of circuits that come from your main electric panel, maybe your sub panel, depending on how big your house is. Those are going to be run, if you have metal studs, they're going to be run in this kind of a VX wire, like this, into your boxes. If you have wood studs, you can use Romex, which is the plastic sheet stuff that you've probably seen at Home Depot. Okay? And those are going to run into your little boxes, which hold your variety of switches and plugs and that sort of thing. There are specific codes that tell you where all of these things have to be in your particular house. It doesn't matter for the scope of this class, but it's enough to realize once you put all the electricity in a particular room, you're again taking up a whole bunch of the space in the cavities of the walls, right? So after you put this in, and after you put all your plumbing in, and after you put all your heating, ventilation, and air conditioning in, then you can actually insulate and cover up those walls. Okay? So once you've gotten to that point, you're going to roll out either batt insulation, right, into the wall cavities. You're going to spray in foam insulation. Maybe you're going to put in rigid insulation, more rare, kind of more specialized. And then depending on where you're building, you may put a vapor barrier in, or you may not. Okay? So another example here of insulating the floor. So this is our fiberglass bat insulation. Everybody relatively familiar with fiberglass bat? Yeah, a little bit. There's an example back there I can dig out of the break. But it's spun fiberglass, and the way it works is you've got all these thin little fibers of glass, and they trap pockets of air. Yeah, it's like this. Okay, it's this pink fluffy stuff. It can be yellow. Okay, not a good idea to touch it with your hands. I mean, I'll touch it anyway. But because it's made up of these really thin glass fibers, right? They have a way of getting into your skin and irritating your skin. So they're just really annoying. So if you're going to handle it, right? I can go over there and I can pet it. It's not going to be that big of a deal. But if I'm actually going to work in it, I'm going to want to have long sleeves and gloves on, right? And probably a respirator so I'm not breathing in these fibers. Okay. And depending on the quality that I buy or how much I spend on it, they may have a craft face, which means it has a paper face. It may be encapsulated in plastic. It just depends. It may have nothing at all. If you're doing attic insulation, typically it has nothing. And this is designed for the ability to actually attach the craft face to the sides of your joists or the sides of your wall, which keeps it in place. Yeah.
Have you ever used like the newer recycled cotton insulation?
Personally, I haven't used the recycled cotton. It's probably more expensive at this stage. I'm not opposed to recycled materials except for blown-in insulation. And we'll talk about blown-in insulation in a second. But for this kind of bat insulation, I'd be fine with a recycled material. The thing about the fiberglass is the fibers themselves are small enough such that they trap air really, really well. And that's why we use it. Okay? So the idea behind the fiberglass insulation is that you've got this network of fibers, right, and it traps little pockets of air, and the air is actually what's doing the insulating. It's not the fibers of the glass themselves. It's the air that it traps. That being said, if you get this kind of insulation wet, right, or you compress it, it loses its insulation value, right, because the fibers come together, you lose your little pockets of air, it's not insulating anymore. Okay, so you have to be really careful with how you handle and how you work with this insulation. Here we are up in an attic, okay, where we're actually putting the fiberglass bats. Same thing. These are not craft faced, nor are they encapsulated. They're just basically the raw material. They're putting these in between the joists. Okay. If you climb into your attic and it's been recently re-insulated, right, you're going to have these bats that were initially put in, and you probably have bats running in the opposite direction, covering them up. Okay. This was a project I did on my own house. Maybe 3 or 4 months ago, because I got tired of paying way too much for my PG&E bill. Right? Yeah.
You put the craft paper facing the living side.
If you're installing before you put the sheetrock in, yes. If you're installing afterward, typically you wouldn't get any face at all. You just have the unfaced rolls, and you use the rolls. There's no real reason for the faces at that point. The face is just to hold the insulation in place. Okay. Any other questions? No. Okay, so this is putting it in underneath, right? Same concept. We're tucking it in between our joists. Okay, the nice thing is that it comes in standard width, so you have 16 inches on center, right? So the fiberglass bats are designed to fit in between those. If you have 24 inches on center, you can buy that. You can also do spray-in foam insulation. Okay, and in this case, they're actually spraying it with a gun. It's a mixture, right? Foams up, and then you shave it off. So this is the knife shaving it off so that it's flush with the edges. Just another method of doing it. Not that common around here. More common, I'd say, up in Canada. Just depends on who's around and who's doing it. Okay. The last type is blown-in insulation, which is usually ground-up newspaper treated with a fire retardant. Very common, very cheap to install. Typically only in attics, not in walls. I do not like this stuff at all because I've worked in plenty of buildings that have this done after the fact. It's great because it's a uniform blanket. Okay, so you can get a couple feet in your attic, right, and it's kind of continuous all the way along. There's no joints in it, right? There's no place for air to infiltrate. But if you ever have to go in the attic to do any work, it is a nightmare. Okay, because you're wading through these couple feet of this insulation. You're kind of crawling through it. You get covered from head to toe in it. It's really bitter tasting, so you have to wear a mask. It gets all in your hair and in your eyes. If you set anything down, it disappears. completely. I've lost flashlights. I've lost tools. Like if you just like accidentally drop something, it vanishes. Okay, and you can never find it. And then you're stuck, weeding through, and then you end up with a little rat body that died a while back, and all that kind of stuff. It's just gross. But it's very common. It's very efficient in terms of how it's insulating. Okay, so just because I don't like it, it's coming from the fact that I don't like working with it. Okay, but it is actually a very efficient way of insulating your attic. Just don't ever crawl in there again, right? Or hire somebody else to crawl in there. Okay, so we talked a little bit about insulation here. This is R19 insulation, which is typical for a 2x6 wall. Okay, this symbol is always for the insulation. And when we look at insulating, right, we're going to fill in the cavities in our wall, but we're also going to want to fill in between our joist and our rim joist here, right, such that there's no break in the insulation. Okay, and we're going to continue all the way down. Also at the foundation, we're going to continue insulating, and then depending on the particular treatment of the basement, you may continue if it's a basement, you may stop and insulate the floor, right, if you have a crawl space, or what have you. Note that there is always that ventilation gap at the top so that the air can come up and out the top. That's important, and it's always going to be there. If you're dealing with a header, okay, if your header isn't solid, right, and it's two separate 2x materials, or if it has a block in between, you're going to insulate in between. The point is, if there's a space in your wall that you can insulate, you should insulate it. Okay, that's basically the principle of insulation. Okay, these are just various corner examples. It's just showing you that I'm actually putting insulation all the way in every space that I have. Okay, if you use the other framing method where you have a framing member here and also here, you're still going to put insulation in the gap from the outside before you cover it up, if you're doing a good job. Okay, if you live in a really cold climate and you can't get enough in your R19, you may thicken up your walls and do another interior non-load-bearing wall just so you can add insulation. So the thing about insulation is you need the thickness to get the higher insulation value. Okay, so R19 is your typical 2x6 insulation. If you move up to 2x10, it goes to R30. Right, you go higher than that, you're going to go into R40, something like that. So you can combine the R values together.
What's your R13?
R13 is 2x4 walls. Okay, so it's not really 2x4, right? It's 3.5 or whatever. Okay, if you do a roof truss system, you're stuck doing the same kind of thing where you really need this insulation here still, right? Recognize you still need your airspace. So the other thing I don't like about the blown-in insulation, okay, since I'm harping on blown-in insulation, is typically you have some Yahoo come in and put this blown-in insulation in because they can do it for cheap, right? And they tend to blow this stuff all the way into the corners, right? And they don't leave this nice little airspace. So if you're putting the blown-in insulation in, you still have to make sure that there's nice airspace, right, that allows this air to flow up in the attic. That's really, really important. Okay, and all too often doesn't happen. This is an airtight barrier. We're not going to deal with this too much if you're trying to get your building airtight from the outside. Typically around here we tend to have our buildings breathe more, so we don't do that. Depends on where we're building. This is a conventional masonry fireplace. The book shows it, so I'll show it to you. If we're in California, it's very, very unlikely that they would ever let you build a conventional masonry fireplace. Because of the environmental restrictions and the pollutants that it causes. So if you have an old house, you might have one of these, which is great. So you can study what it looks like on the inside if you want. But typically you're going to have some kind of a more efficient wood-burning stove or something that's actually inserted to look like it's a fireplace. Yeah.
And that's the question about the, there was a couple slides back.
Yeah.
And this is something I've seen more often, is this raised heel truss providing the airspace. Isn't that more common than that other airspace,
Is this
it's
the slide? Right.
slide you got right here.
Right.
Than this.
Right. This is so. Good question. Sorry, I have to hobble. Take
Yeah,
that
no,
off.
that's right.
So this is a good question. So what you were asking is, in this particular instance, right? This is if we had a wood frame building where we're building it, putting our own rafters in. This is much less common. I think I heard a statistic saying 75% of the buildings that are going up today are having roof trusses like this. If it is a roof truss system, right, it's very much the same way that you're going to worry about insulating. The thing about it is, in this instance, the ceiling is flat, okay? So you're not dealing with the insulation going up like we were in the other slide. In this instance, we're running right across the ceiling. So it's treated virtually the same as if it were just the ceiling joist, and we're filling in the insulation. Same thing happens, only this time it's a truss. And we just have to make sure that the insulation doesn't extend too far such that it blocks this so that we have a little bit of airspace. It's pretty easy to judge because usually these are 2x4s. So as long as you don't cover up that last little bit of the truss, you're safe in terms of insulation. But you still need to insulate with it. Okay, let's see. So that was a fireplace. That was enough of the fireplace. Okay. Interior doors, just a couple terminology things, just so you're aware. This is a Z-brace door, very uncommon. The 4 or 6 panel doors tend to be the most common in this day and age. Sometimes it's a 2-panel where you have a big bottom panel and a big top panel. Depends. When you go home, you can look at it. A little bit of terminology. On either side, we have what are called stiles, run down the outside. We've got rails, which are the horizontal pieces. Stile goes down the middle. So same thing here, stile, 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 right? Rail, 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 rail. You can have a flush solid core door. This just means it's solid, okay? And you can also have a flush hollow core door. So if it's a really light door, it's probably a hollow core door. Note that there's a little bit of extra blocking around where the door latch set actually goes. Okay? Interior door installation, virtually what we talked about before, so we don't need to go through it. Interior stairs, important terminology is this, that you have a stringer, variety of different types of stairs. I'm not really going to test you on stairs, I just want you to be aware that stairs exist in buildings. Right? A little bit more terminology, right? A tread is what you can put your foot on. A riser is what?
Stub your toe.
Right, you stub your toe on, exactly. Okay? The interesting thing about stairs is there are certain tolerances for how much a stair can vary, stair to stair. And if you have more than a 1/4 inch, you will notice. Is there any stair that you typically trip on, that you always trip on? Okay? Even though you know that that stair trips, right, you still trip on it? Because after 2 or 3 stairs, your body knows the correct distance for each stair. And if it varies by more than about 1/8 of an inch, so if you're in a 1/4 inch, something like that, you're going to trip because your body's anticipating that certain distance. It's really kind of bizarre. So, because of that, we have certain tolerance requirements such that the stairs have to be a certain consistency. Stair to stair to stair, right? Otherwise we trip. Okay, a little bit about moldings. There's a whole bunch of moldings. They're all shown up over here too, that you can see them. Okay, I'm not going to test you on what all of these are. I just want to kind of point out what they are. Crown moldings typically are at the ceiling. Okay, base is typically at the bottom. Yeah. No. Chair rail is typically in the middle. These are the chair rails here. A variety of other pieces. These are our bases. Right? They're always going to vary. Our chair rails and our picture moldings, these kinds of things, are all along the middle of the in the middle of the wall. So we've got base, we've got chair rail, we've got crown. These are door and window casings, the trim that goes around doors and windows, and then we've got handrails and closet poles and that sort of thing. Yeah.
What's the purpose of chair rails?
In the old days, chair rails was it was a nice solid strip of wood such that if you scooted your chair back, the back of the chair wouldn't dent the wall. That was the original purpose. It has evolved into just being a decorative piece. So if, for example, we walk back to the back of this room on this wall, right, it has a nice little ugly chair rail for us that they conveniently put on here. It's a little bit low in my definition of a chair rail, but it is here. They put it on for decorative purposes. They were not worried about you backing up into it. But this is something that ends up being very common. This room doesn't have base, so we don't have any base and we don't have any crown.
It's higher over there.
Oh, is it higher over there? Yeah, real good construction job in this class. Okay, so we've got, these can be made from solid wood. They can be also engineered wood, like medium density fiberboard. Just depends.